Okay. First of all, thanks to the organizer for the invitation to the Asymptotically Safe seminars and opportunity to talk about this work that we recently put on the archive. The title of the paper is, as Mark told, Scaling Solution of Matter Form Factors in Asymptotically Safe Quantum Gravity. And is based on a collaboration with Alfio Bonanno, Emiliano Glaviano, and Frank Sauer-Sippi. So, brief basic introduction that probably you have heard many times. General relativity as a quantum field theory is perturbatively non-renormalizable. What does it mean? It means that new divergences emerge at each order in the perturbation theory. This has been shown about loop by Toft and Vedman, at loop by Gorov and Sagnotti. That means that there is no predictive power in general relativity as a quantum field theory. A possibility to solve this problem is the asymptotically safe quantum gravity conjecture by Weiberg, proposed by Weiberg at the end of the 70s, according to which gravity could have a non-perturbative fixed point in the UV. What does it imply? It implies that in the UV, the RG flow of the Newton constant hits, in its dimensionless form, hits a constant value. And if the dimension of the critical surface of the UV attractive critical surface of this fixed point is finite, that means that there is a finite number of relevant operator near this interacting fixed point, we have restored the predictive power of the quantum field theory associated with quantum field theory. To study this scenario, a non-perturbative treatment of quantum field theory and the renormalization group is required. And most of the work in the past years has been done using the Wetterich equation that is written here, and you already know very well. But thanks to this equation, we have strong evidences of the existence of a non-perturbative fixed point in gravity, called the Reuter fixed point, both in poor gravity and in gravity matter system, including even the standard model. Many authors collaborated to this result. It is the asymptotically safe quantum gravity research direction. There are some names, but of course they are just a part. However, in this work, we used another renormalization group equation, that is the proper type renormalization group equation. And before discussing our real actual computations, I will try to make an introduction and discuss the feature of this RG equation. So it was first introduced by Percacci and Florianini and by Liao as a flow equation for the effective and average action gamma k, the same object of the Wetterich equation. How is it introduced? How is it justified? At one loop, we have this is the expression of the one loop quantum effective action when we have this trace, functional trace of the logarithm of the Hessian of the bare action S. We can rewrite this logarithm as an integral over the so-called Schwinger proper time S in this form. And at this point, we can introduce our regulator that is necessary in order to make this integral finite and meaningful in this proper time integral. So we introduce a regulator that we're gonna call rho that regulates both the UV via the quantity lambda square and the IR via the quantity k square. And we obtain this new regulated form for the one loop quantum effective action. And now we can make a derivative with respect to the IR cutoff k and derive this flow equation this one loop flow equation here. Via RG improvement, we can turn it in a closed equation where we replace the action of the Bev action with the action of the average effective action gamma k. However, it has been shown back in 2002 by Leahy and Pawlowski that this form here, this equation, is not exact, while the Wetterich equation is one loop exact. To understand better the difference between the two equations, we can try to write the Wetterich equation in a proper let's say proper time form. To do this, we apply the same transformation of the proper time transformation to the regulated propagator that appears in the Wetterich equation. We obtain this expression here, and we want to reduce it to the proper time form. To do this, we have to separate the two terms in this exponent by separating the regulator to this, so we can rewrite the equation in this form with this R-cursive regulator, where R-cursive is given by the derivative s time the logarithmic derivative of the regulator times this the exponential of the regulator itself, plus this complicated function k that is basically the Becker-Camper-Hausdorff relation that allows us to rewrite this exponential of the sum of as a product of two exponential. In general, this recursive function is different from a proper time regulator. For the derivative of the proper time regulator, that from now on we'll call R, because as you can see here, this recursive term depends on the full interacting two-point function. That depends on the fields and so on, while we have no trace of this in the proper time regulator. So this dependence, the absence of the dependence on this regulator, as a consequence, the inexactness of the proper time equation as an average effective action flow. In some approximation, for example, in local potential approximation, where we consider the fields as constant, the regulator commutes with the interacting the two-point function, and so all the function k that is basically built on commutators between these two operators, as you know from the Becker-Camper-Hausdorff relation, goes to 0, and so on. So one can establish a map between some Wetterich regulators and some proper time regulators. However, the flow of the average effective average action is not the only approach to the study of the RG flow of a theory. One can also use the flow of the Wilsonian effective action. Here I will briefly resume the difference between the two approaches. The effective average action is a quantum effective action can be seen as a series of quantum effective actions of theories with an IR cutoff. The one loop exact flow requires this particular structure here, where the derivative of the effective average action is proportional to the trace of the regulated propagator gamma 2 tilde, where theta OK is the regulator and O hat K is the derivative of the regulator in the case of the Wetterich equation. the relevant limit of the effective average action are the full quantum effective action for k to 0 and a fixed point gamma star, hopefully, for k going to infinity. It generates one point irreducible correlator. So all quantum correction for modes above the cutoff scale k are already included in the correlation function generated by this functional. As already told, the most used exact equation for the flow of the effective average action is the vectorish equation that you know very well. On the other hand, we have the Wilsonian action. In this case, the Wilsonian action S lambda is an effective action with a UV cutoff. The algae flow of the effective action is generated by requiring that the final partition function is invariant with respect to a change on the cutoff scale lambda. And this is equivalent to saying that the derivative with respect to the scale lambda of the exponential of the Wilsonian effective action is equal to a total derivative of the field in order to give 0 up to boundary terms that we neglect in the path integral. So we expect the derivative of the exponential of the Wilsonian effective action to have this kind of form, where this function psi, function psi, is called the Coles-Graining operator. The relevant limits are for lambda going to 0, all the modes are integrated out, and we recover the partition function. On the other end, for lambda going to 0, we have what we usually call in quantum field theory the bare action, that is the action non-quantized in the limit of infinite where we remove the cutoff. S lambda is a bare action in the sense that to obtain correlation function between field below the cutoff scale, we still have to do all the loop expansion and calculation, or whatever you prefer. But the loop integral will stop at the scale, at the UV cutoff scale lambda. Example of algae equation for the Wilsonian action are the Polchinski equation or the vector autumn. The reconstruction problem, that is the problem of relate the fixed point Wilsonian action that correspond instant limit to the bare action with the fixed point effective action, effective average action has been studied, for example, by Reuter, Manrique, Morris, Platini, Savoresing, and order in the literature. So we have seen that the proper time renormalization group equation is not exact as a flow for the effective average action. However, in 2017 by the Alvis, it was suggested to use this equation as a Wilsonian algae equation. This is the corresponding form. It's very similar to the one we saw before. The difference is the minus in front, and now we make derivative with respect to lambda and not instead of k. Is in this form the equation exact? This question is equivalent to ask whether for right-hand side f, where we call f this right-hand side of the flow equation, there is a Coles-Graining operator psi, such that the right-hand side f can be rewritten in this form here that grants the invariance of the partition function by change with respect to change of the cutoff scale lambda. In 2019, by Bonanno, Lippold, Percacci, and Bacca, it has been shown that there is a formal solution for this problem. There is a coarse graining written here. It is quite complicated expression. We can go through the pieces quite quickly. Here, f twiddle is a generalized Fourier form of the right-hand side of the algebraic equation. The dot operator represents the product under the integral over space, d-dimensional space time. I mean, we are in Euclidean, so d-dimensional space. G is the regularized propagator of the regularized theory, Wilsonian theory. W here is an arbitrary function. In fact, this solution psi of psi, this coarse-graining psi is not unique. However, by requiring some boundary condition, we can, for the problem, we can constrain this W. For example, one can ask the coarse-graining to go to 0 for the field going to infinity in order to keep the potential convex and the theory stable. So, okay. So in general, the proper time minimization group equation can be seen. Okay.
Oh, yes. Sorry for interrupting you, and I might be misunderstanding something, but how can this equation be exact if it's simply one loop ansatz for the effective action that you've simply plugged in, and you study the flow of the one loop effective action? I mean the first equation on the previous slide.
Yeah, I mean this is in the form for the quantum effective action. It is not exact because it can be shown that in general it does not structure here. It does not depend linearly on the algae regulated propagator, but depending on the cutoff, it depends in different way. However, as a Wilsonian algae equation, it is exact. It can be exact.
What do you mean by exact? Like it is just equivalent to the functional integral, or you mean some sort of one loop exact?
One loop exact.
Yeah, so it's no different than doing perturbation theory, right? But the
No,
calculate
it means that at one loop, even if it appears at one loop in the form, it actually includes all the collection. I mean,
so the results you get, like from perturbation theory, for example, I don't know, like you get one loop, beta function, and you compare with this, the results of this equation, they're not the same, right?
if you use the full interacting form of the ansatz of your Wilsonian action, no, they are not the same. I mean, there are some regimes where you cannot do perturbation theory if the theory is interacting.
Okay, okay. Thank you. Sorry for interrupting.
No, thank you for the question.
Can I actually also ask a quick question about this, since we are talking about the exactness of the flow? My question is, do you hear me? Am I frozen?
Yeah.
So this now, you're saying this is an exact equation for the Wilsonian
Yeah.
flow. So does that mean that you generate also connected and disconnected diagrams, and that you have to arrange the disconnected diagrams in a specific way, or how does this work?
I mean, I'm at the moment, I'm generating the correction to the bare action at the scale lambda. Then from this, I will have to extract to generate correlation function. I will have to to do all the usual stuff that you do with a direction. That is, I mean, you compute a partition function and so on. I don't know if it is what you were asking.
No, I was just asking on a intuitive level. So your right-hand side generates connected and disconnected diagrams.
A priori, I think yes, but then the correction to the action are only given by the connected ones, because then you reduce to this form that is the correction to the S, that is the logarithm of the partition function. So I think that this generates the connected one.
And the disconnected ones are trivial, or why?
Because
if you're Wilsonian, you would need the principle to have all the diagrams connected and disconnected.
I mean, you have the disconnected if you are writing okay, if we're writing the algae flow of this quantity here, this requires also the disconnected one. If you write the algae flow of the exponent only, you need only the connected one.
Okay, and so you have in the end the flow of the exponent.
Yeah,
you're saying that. Yeah. Okay, thanks.
Yeah, here, but we have both the 1 point reducible and the 1 point irreducible. This is different with respect to the
But the flow of the 1 PIs, they're not exact, or how does this work? I'm just a bit confused about these. Because
yeah,
you said the 1 PI is not exact, but the connected one is exact.
Yeah.
Okay, thanks.
You're welcome. Okay, so another point is crucial in this kind of algae equation is the choice of the regulator. In general, how does it work? A regulator, we choose a cutoff in order to cut the momenta in a Wilsonian energy. We want to choose a cutoff in such a way that we consider only integrate only over the momentum scale up to a given scale. So in this equation, we will say that we can see that the regulator here suppress the modes with S smaller than 1 over lambda square. The trace in momentum space suppress the modes with P square larger than 1 over S. The result is that the modes with P square larger than lambda square are suppressed. And so we are selecting the momentum mode. We're integrating only on the momentum mode above. We maintain only the we maintain only the momentum mode below the cutoff. However, if we have a wave function renormalization, this relation is changed, and I mean we don't want it because it changed it is not in accordance with our interpretation of the Wilsonian algae process, the Wilsonian cross-graining process. And to avoid this discrepancy given by the Z factor here, we can use some spectrally adjusted regulators. In particular, we will use two possibilities. One is to introduce the dependence on Z, the factor Z in the cutoff, and make a total derivative with respect to lambda of it. This will give a term proportional to the anomalous dimension of the field. The other possibility is to introduce the factor of Z in the regulator R, that is the derivative of the cutoff law. In this way, we have the type C regulator where we don't have dependence on the anomalous dimension. In both cases, in the type B regulator and type C regulator, now we can rescale the proper time as a factor of Z, and we recover the initial form written here. Here we have the anomalous dimension, here not. But again, we are cutting on momenta at the scale lambda. So we have recovered the meaning of integrating on momentum shell that we like, let's say, where, yeah, eta is the anomalous dimension. Yeah, so we have these two choices. Let's turn now to closer to our practical computation. We would like to go beyond finite truncation and derivative expansion. To this end, a very useful formalism is the form factor one, introduced by Lipton and Saueressig, but many others also work on this direction. This is an example of gravitational effective action with four factors. We have a four factor for curvature squares, term for gravity, a four factor for the kinetic term of the scalar field, and we can go on introducing our other interaction with more form factors. This approach allows us to have a full momentum dependence in a covariant way, to go beyond RG improvement, because we don't have to do identification scale between the cutoff scale and the momentum scales, which are not which can be ambiguous when we have more than one energy scale in our problem. They permit to study asymptotically safe amplitude because they preserve the full momentum dependence of the amplitude, and can permit us to make prevent analytical continuation, but even to study genuine non-local theories. So our setup, we decided to start from the simplest one, let's say, where we have GR plus a scalar form factor, which we decided to take F canonically normalized, the form factor canonically normalized. That means that the derivative with respect to box of F computed at zero momentum is equal to 1, and the meaning of the other freedom is absorbed in the field normalization Z of lambda. This model was already, the setup was already studied by the FRG, like Lipton and Saueressig in 2019, and so we decided to approach the same problem with the proper time RG. We will use linear splitting in the Donder gauge fixing term, and the ghost term. And we will use this class of regulators that depend on the parameter M, that has to be larger than d half and entire. This is the regulator given by incomplete gamma function, and the resulting this is a cutoff, and it is the regulator R given that by the derivative with respect to lambda of this cutoff. Okay, so we start from the total equation of the gravity sectors. This one has been treated in the background approximation, as already done by Bonanno and Reuter. Bonanno, Giorò, and Zappala recently with interesting analysis of the gauge dependence and cutoff dependence and so on, but also by many other works that I won't stay here listing, but yeah. So we can write the flow equation as a sum of three contributions, one from the gravity part, the gravity interacting two-point function, the scalar part, and the ghost part. We can expand this Hessian as a kinetic part plus an interaction term in curvature, which contains curvatures for all the term, where now the gravitational part has been separated in a tensor part and the scalar part. And now we can compute the functional trace of the various operator dependent on box using the kernel expansion for a generic function W of the box operator. We have this expression here, where we have the terms of the hit kernel expansion of box, which are contribution to the ontological constant, 1/6 the curvature scalar, times this function q of w written here. We want to study the flow of the Newton constant, so we look at the term proportional to the curvature scalar in the right hand side. This gives this equation here. This is the gravitational and Gauss contribution, and this is the scalar contribution that depends on the form factor. This term here with the anomalous dimension and this term here with the anomalous dimension appears only if we use a type B regulator, that is the one with the dependence on the anomalous dimension. Yes?
Yeah. Why is that each term of the Hessian or the action gets its own regulator? And I mean, why did you split the action like that? I mean, those are operators, they don't commute, so in general, your exponential of the full action does not equal to the product of exponential. So, sorry, what did you do here?
I'm separating the component of the trace. I'm doing a trace.
Okay. Okay, yeah. And why are regulators different?
Because we are using this kind of one moment. Spectrally adjusted regulators. So the regulators in some way depend. If we use a type B regulator, it will depend on the anomalous dimension of the field, and different fields have different anomalous dimension. So we have to consistently adapt the regulator to the field that is propagating in the loop.
Okay, yeah, I get it. Thank you.
You're welcome. Okay, we get this expression here. Now we move to the probably more interesting part, since it's the new contribution, is the scalar form factor. This is the flow equation. We extract the beta function of the form factor by applying the second functional derivative to both hand side of the algae equation. And to algebraically compute the object, we can remember the fact that the proper time integral is actually a regulated version of the usual it-kernel functional trace. And I mean, we know for the literature how to expand and how to compute functional derivative of the it-kernel traces. So in the one loop correlation with the it-kernel, we have again this expression for the one loop effective action. We make the proper time, we move to the proper time expression. We inflate the ground. We decompose the action as a function of partial derivative plus an interacting term, and then we expand in vertices. This action, and for example, for the second derivative of the one loop effective action, we get this expression here, where the first term here is a Talbot diagram, while the second term here is equivalent to a bubble diagram, or however you prefer to, candy diagram, or whatever you prefer to call it, where we have two propagator, 1 and 2, and two free vertices here, V prime and V prime. While here we have a 4 vertices, 4-point vertex, V second, and only one propagator given by the exponential form. So we plug the regulators, and we repeat the same procedure that was used to obtain the expression I showed you before. And what we obtain is this expression for the flow of the form factor here. Again, we have the tadpole, the bubble diagram, and the relevant differences are basically these the regulator here, R of eta and R of eta graviton and eta scalar. What are them? Sorry. In the tadpole, we have only one propagator, so it is quite trivially the spectrally adjusted regulator that I showed you before. So in the C scheme, it's just the R of M function. For the B scheme, we have also the anomalous dimension term. The things are a bit more complicated in the bubble diagram because we have two different propagators in the loop, and the two propagators can be associated to different fields, which are regulated in by different regulators. And so, I mean, in the C scheme, there is no difference. On the B scheme, we have this more complicated expression here with one part proportional to one regulator, one anomalous dimension, and another part proportional to another anomalous dimension. If the two are equal, we see immediately it is reduced to this form here. And a way to interpret this expression is that in this reparametrization of the loop integral, xi, the parameter xi, represents basically which portion of the proper time, of the finger proper time is spent doing the loop in one propagator and how much time is spent in the other propagator. So we proportionally regulate the proportional fraction, the relative fraction of the proper time with the right regulator with the right anomalous dimension. From this, we obtain these xi and 1 minus xi factors in front of the anomalous dimensions. The vertices of the form factor, the generic form factor, are extracted in following the procedure developed again this work, very interesting work. And the equation for the scalar anomalous dimension is obtained by enforcing the constraint that the form factor is canonically normalized at all scales. That means that the derivative respect to p squared of the form factor computed at p equals 0 is 1 at all scales, and so its derivative with respect to lambda is 0. We want to look for fixed points of the energy flow. So we move to dimensionless quantities, and as right here we have the dimensionless Newton's constant, the dimensionless momentum, the dimensionless form factor, and the dimensionless anomalous dimension. Or all the quantities are made dimensionless using the algae scale lambda. The fixed point equation requires that the derivative of the fixed point are 0, and consequently it is equivalent to require that the gravitational anomalous background anomalous dimension is equal to d minus 2, and while the fixed point equation for f star has this form here, where there is the dimensional scaling, the scaling given by the classical dimension and the anomalous dimension, with the implicit dependence via the dimensionless momentum x, and then we have this function x, this h, that is basically the right-hand side, the dimensionless version of the right-hand side of the proper time equation. Yeah. So in scale, we can write the form of the fixed point value of G star. It has this form in the scheme C and this form in the scheme B, with the usual at this point dependence on the anomalous dimension of the scalar. However, to obtain a solution for the fixed point of the form factor is more complicated, and to obtain this this result, we need to use numerical method. In particular, we've used pseudospectral methods. First step, we compactify F by introducing this F twiddle that range from -1 to 1 with L equal, if we choose L equal 1. If F star goes like x to the power a at infinity, and we choose gamma larger than alpha, sorry, not a alpha, of course, then F twiddle will be bounded. We will take gamma equal to 2, and we will see later on that is a good choice. Now we expand F twiddle in Chebyshev polynomial with coefficients Cn, and evaluate the system of the equation in our Gauss-Lobato grid of size n. We get a system of equation for the coefficient secant n, g star and n star, where we have exactly where we use as equation as constraint also the canonical the property of being canonical of the form factor, and the constraint on having the background gravitational anomalous dimension equal to 2. We solve this problem numerically, and these are the results here for the cutoff C, n equal 25, and the different values of m. We can see here how the parameter depends on different m. See that anomalous dimension and the behavior alpha that is more than 1, so than 2 is smaller than 2, so our choice of gamma equal to was correct, was compatible. And here the asymptotic behavior of the form factor compared to the trivial one f of box equal box. We see that we start from 0 momentum, so we don't have a mass gap in the fixed point solution. Here we can see the stability with n, with the truncation n. We check for different truncation at m equals 3, how the fixed point change at different n for various values of x, and we see that the shift with n decreases quite quickly, and the same happens with the variation of the fixed point value g star and the scalar anomalous dimension eta star. These are the results for the cutoff B. They are quite similar, as you can see. We also have quite good convergence. The next step is to compute the stability matrix and the critical exponents. So you consider linear perturbation near the fixed point for the dimensionless Newton coupling and the form factor. We decompose the variation of form factor again in Chebyshev polynomial delta C n, and we solve the eigenvalue problem for the stability matrix. We get a set of eigenvalue lambda I, and the critical exponent are given by minus the eigenvalues. Here we can see a plot of the critical exponents at different truncation in n, in the Chebyshev polynomials. For both cutoff B and C, we have 2 relevant direction. We associated the largest one to perturbation of G, and the smaller one to the mass perturbation of the scalar field, and an increasing with n number of irrelevant directions, which, however, seems to remain irrelevant. That is quite good because we have a constant number of relevant, constant dimension of our critical dimension. Finally, the last comment, the emergent locality of direction. What does it mean? The direction is recovered when lambda goes to infinity at fixed p. So we take the correspond to x, the dimensionless momentum, going to 0. we have imposed f star prime as 0 equal to 1. So we can expand the form factor in this way for smaller x because of its analyticity. That implies for the dimension for factor this structure here with p squared plus terms of the Taylor expansion. So in the limit lambda to infinity, we have f star going like p. So even if the fixed point is for factor is in general non-local, in the limit corresponding to the bare action, it is local. So we come to the conclusion. The proprietary normalization group equation can be used as an exact Wilsonian algae flow. Using the vertex expansion of the kernel, we can retain the explicit momentum dependence through form factor. In the GR plus scalar field with a form factor, we find a fixed point. There are two relevant directions, different truncation order and cutoff choices. The form factors in the associated bare action is local. Possible outlooks are that to include the cosmological constant in the computation, to include also form factors for gravity in a closed form. A first step has been done by Glaviano recently, by Emiliano. Introduce a new adjusted cutoff that cuts on z of f of minus box, because in this moment we are because of the form of the nonlinear structure of the form factor with respect to p squared, we are again not actually cutting over the at the scale p equal lambda. So it will be interesting to check whether these give differences and which kind of differences, which are the effect of having a regulator that actually cuts at p square equal lambda square. And finally, a better understanding of the reconstruction problem that relates the two fixed point of the effective rejection and of the Wilsonian action. Thank you. That's all.
All right. Thank you very much, Diego, for the nice talk.